Okay, so we are going to discuss acids and bases. It does say acid-base equilibrium intro, but we are going to make sure that everybody's on the same page about or from the acid-base concepts you were supposed to learn in grade 11. Okay, so last year, actually in grade 10, your grade 10 teacher probably gave you a very limited definition of what an acid and a base are and neutralization. So they probably said things like an acid and a base make salt and water, which is fine. However, that is not always true. So what we're going to deal with this year, and we just did the definition of them last year, is quantitatively, how can you tell whether something is strong or something is weak? So for example, hydrochloric acid is a strong acid. We use it in the lab to eat away at metal, right? You guys saw like a 20-degree temperature change when you put magnesium in with hydrochloric acid. Obviously, that is not the same acid like vinegar that we put on our French fries, right? And then put inside our stomachs. So there has to be something going on. Yes, it can be that it's less concentrated, but there's also a pattern of dissociation. So we're going to write dissociation equations, which will look similar to what we did for the solids that we just did, except now we're going to start with an acid and we're going to start with a base. So SA stands for strong acid. And SB for strong base. And that, when you react to strong acid with a strong base, you are going to get a perfectly neutral solution of salt and water. However, if you don't have something that is strong, so if you have, for example, a weak base, then you're going to get what we call an acidic salt. So a salt that's a little bit more on the acid side, so a lower pH. And then if you have a weak acid, you're going to get a solution that's a little bit more basic. And it all has to do with what is the concentration of hydrogen ions that are transferred. So last year, we would have talked about proton transfer in a very qualitative way. Now we're going to say quantitatively, using an ice table equilibrium constant, how much or what's the concentration of hydrogen ions produced or consumed. Okay, so in general, acids are sour. So things like vinegar, citric acid, like citrus fruits, those would be considered weak acids. Not that you should taste the acids in the lab or anything like that. They do make ions. They do dissociate into plus and minus, which means they will conduct electricity. So we often talk about the dangers of batteries because they have battery acid or sulfuric acid. So if it's in a battery, then it's going to help or provide a path for electron flow. They cause certain dyes, which we call indicators, to change color. So in grade 10, you probably did a lab where you used pH paper, bromophenol blue, which was yellow and blue, phenolphthalein, clear and like hot pink, fuchsia, sometimes we say. And then some people will say that acids feel corrosive. So is corrosion a feeling? I don't know, but definitely you could, if you get an acid on your hands and or in the lab or whatever, and it's strong enough, you will definitely feel it. And then the first most basic indicator is called litmus paper. It turns litmus paper red. Bases have a bitter taste. So perhaps soap is, generally speaking, on the more basic side. If you've ever had your mouth washed out with soap, you'll know that bitter taste. Another example that maybe you've experienced is if you've ever taken Tylenol or aspirin without the coating on it, and you put it in your mouth and you leave it too long, that weird taste. It's because it's basic, so a bit weird, bitter taste. Generally speaking, our taste buds, our bitter taste buds, that's not a good thing. We don't like bitter taste. They will also conduct electricity. They dissociate into ions, just different ions. They will cause an indicator to change the opposite color to a base. They do feel slippery or soapy. So if you have what's called lye soap, L-Y-E, maybe at your, like if you have a laundry tub, or if you have an old school grandma who like hand washes stuff, like scrubs them, it's got like, you can literally kind of see the lines in it. It's super harsh soap, but it is mostly sodium hydroxide. Same thing with Drano, is usually very basic. So this can be a little bit dangerous because bases will denature proteins or break them down, but you don't feel it right away. It just feels like soap. So when you have harsh chemicals that are supposed to be for cleaning, like Drano is a really bad chemical. Like, you shouldn't mess around with it unless you have a severely clogged drain, because you can get it like in your eye or whatever, and lose your eye, but it wouldn't even really hurt until it was too late. Okay? And they turn litmus paper blue. There are two theories of acids and bases. We'll talk about Arrhenius first. Again, we did talk about this in grade 11, so maybe you remember his name. This is supposed to be a hydrogen. So he said that acids dissociate to produce hydrogen ions in solution. That is true of every single acid. So an acid is an acid because it produces hydrogen ions. So any solution that produces hydrogen ions can technically be considered an acid. So that's why we need the further distinction. And why can we put vinegar on our French fries, but hydrochloric acid eats away at that magnesium metal strip, right? So it has to do with how much an acid dissociates, or a base, okay? So if something is strong, then it dissociates 100%. So what that means is, technically, HCl, aqueous, this doesn't even really exist. Every single hydrogen chloride molecule has been split apart or dissociated into hydrogen ions and chloride ions. Notice this is not a double arrow. It goes 100% to the right. When we look at the actual Ka values for these acids in the chart, it'll say in the book very large. It doesn't even give a number because it is not considered to have reversibility. So one of the questions in the homework, I think it's nitric acid, which is a strong acid. and it talks about what's the concentration of HNO3 or nitric acid in the solution, and the answer is 0. So the reason is because there is no reforming the reactants. This reaction does not go in the reverse direction, it only goes forward. So the ion concentration is, it overtakes the system. Equilibrium is not established. So when you have something that's weak, whether it's a weak acid or a weak base, then it only about 1% dissociates. So this is a little bit, this isn't absolute like the first one is. So this is where we're not really sure. This means about 1% dissociates. So in this case, now equilibrium is established. So in a system, there will be some of the acid and some of the ions it produces, which means there is reversibility, so we have to do ice. So today, we're just going to do questions based using pH and things like that for strong acids or bases. And then on Monday, when we come back, then we'll look at how can you calculate and how can you tell what percentage of that weak substance has dissociated. So if acids are acids because of the production of hydrogen ions, a strong acid is so strong because it produces the maximum amount of hydrogen ions versus a weak acid like vinegar or ethanoic acid, acetic acid. It does not. It only produces a little bit of hydrogen. So you get a little bit of bite, right? Vinegar, maybe gets your tongue a little bit, but it's not going to corrode it or corrode your esophagus or anything like that. Because it makes less hydrogen ions. Okay, so Arrhenius, his theory was good. And then when we get to bases, his theory starts to have limitations, okay? So he said that bases have to have hydroxide ions, and they are going to be a direct source of them when they dissociate. So that is only true of strong bases. So a strong base can be identified by the fact it has OH in its formula. Sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide. But there are substances that will neutralize or make a solution less acidic. So they behave like a base, but they don't have hydroxide in their formula. So we needed a broader definition of what a base was. Arrhenius isn't wrong, his theory was limited. So in grade 11, one of the, in a normal situation, one of the things would be just like compiling a list of strong acids and strong bases. So strong bases are easier. They have hydroxide in their formula. And then we made a list of strong acids. So on Monday, what we're going to do is we'll look quantitatively how you can tell which is which, okay? So basically, if you're given a Ka value, then it's not going to be strong. So today, when you do the questions, none of them will have any sort of information about like the Ka value, equilibrium. It's not going to talk about equilibrium at all because the reaction does not go in the reverse direction, which makes your math a little bit easier. Okay, so then we needed a better definition. So this is very important. Bronsted-Lowry. So they even will sometimes talk about like a Bronsted acid or Bronsted base. And what you'll find is moving forward, should you continue in chemistry, you're going to often talk about reactions in terms of proton transfer. So the reason we call the hydrogen ion a proton, and you're going to do this in biology as well. So let's say you have hydrogen, Hydrogen has an atomic number of 1, so it has 1 proton. Its mass is 1, so 1 minus 1 means 0 neutrons. And then in the first column, it's going to have 1 electron. So if you're going to make the positive ion, that means lose electrons, yes? So what you're left with is a proton. So a hydrogen nucleus, which you might hear it called that as well, the hydrogen ion nucleus, is just a proton, no neutrons, and it's lost its electron. So inside our bodies, then our muscles make, or not muscles, just muscles, our cells make energy because we create a proton pump. We pump protons across cell membranes to create a concentration gradient, which drives the electron transport chain to make energy for our cells. So should you take biology, then you'll talk extensively about pumping protons across membranes. We do it all the time. There are many, many, many reactions that can be written as proton transfer. So instead of saying an acid-base reaction, I know that in grade 10 they often just call it neutralization. Technically, a much better term is proton transfer. So if you continue with chemistry, then you'll talk about many reactions in terms of are they losing or donating or gaining or accepting protons. So proton transfer is a much better way of describing these reactions. So an acid is a proton donor and a base is a proton acceptor. So this, tonight, I forget, the other day was products over reactants. Tonight it's going to be acid is a donor, base is an acceptor, until your guardian parent, your loved one, sibling, whatever, comes and says, be quiet and go to bed, okay? So it is very important to remember which is an acid and which is a base. Last year, all you had to do was take a look at this equation and label the acids and bases, and then we'll talk about the conjugate acid-base pairs. Eventually, you guys have to be able to write your own dissociation equations. But in this year, we're only going to do 1 proton being donated or accepted at a time. You can get a little bit more complicated, but we're just going to keep it simple, okay? So let's just take a look at this example. I think I didn't take it from your grade 11 note, but I feel like it is in there. So now we look at this, and yes, you might recognize this as hydrochloric acid, but just humor me for a second. So what they noticed was this reaction produced a solution that was less acidic or less basic, depending on what they started with, based on the pH scale, than before. So none of these have OH in them, so they couldn't use the theory that all bases have hydroxide to explain what was happening here. So you have to think of it like acid, or think of it as proton transfer. An acid is going to donate a proton, and a base is going to accept a proton. Last year, you guys considered what happened in the reverse direction, but we didn't really talk about it being an equilibrium equation too much. But now you know there are many reactions that actually can go in the reverse direction. So one of the things you have to be able to do is label what's an acid and what's a base, okay? So you're going to look at what it is and then what it becomes, okay? So logically, this and this are not related, right? So you look at the substances that are related. It makes sense that this NH3 has done something to become NH4. And it's 50-50. It either gave away a proton or it got one more. Okay? So you look, NH3, NH4. So you can look at a couple of things. This is a 3. This is a 4. Is that more H's? Yes. This has a charge of 0. This has a charge of positive. That also goes with a proton, right? Protons have positive charges. So you could look at that as well. So this ammonia accepted a proton. So it is the base. So you can write B for base. You don't have to write the whole word if you don't want to. You don't really need to explain it either, but if you want to explain it here so that you can go back and look at it. So if the NH3 is the base, then logically HCl has to be the acid. But let's just look at what happens, okay? So now we have HCl, and it makes sense that it becomes Cl minus. So here it has one H. Does it have any H's here? No. So it is the proton donor. Generally speaking, so these both have H's. Sometimes that can be a little bit tricky. Usually one of the substances, it's really obvious. This is HCl. Now it's only Cl minus. Obviously, there's less H's, okay? But now we also have to go backwards. So every single substance should be labeled as an acid or a base. This reaction can go in the opposite direction. Okay? So again, it's really 50-50. If this is a base and it became this, then if you're going to go the other way, then logically this can't be a base as well. That doesn't make any sense. It accepted a proton, but it's going to accept again. That's not what happened, right? So this NH3 gained a proton to become NH4. Now this one is NH4. Over here, it's NH3. So it got rid of an H. On the product side, usually, again, this doesn't have any H's. Okay, so usually one of the substances is very, very obvious. This cannot donate any H's, it doesn't have any. So this has to be the base. We're going to do more, okay? So arrhenius acid and Bronsted-Lowry acid are the same thing. Acids have to have hydrogen. But a base can be anything, any anion, really anything that can accept an H+. Anions are negative, so negatives and positives, opposites attract in chemistry, right? So that's straightforward. But again, ammonia is a very, very common weak base. And so it's a little bit tricky because it already has H's, but again, it can form the ammonium ion. That's a thing that you've dealt with before. So like I said, when you talk about acid-base reactions, you really shouldn't say neutralization. You're going to talk, moving forward, about proton transfer. The acid donates a proton to the base, or the base removes the proton from the acid. And it's tough because we're used to thinking of acids like dangerous, right? But really anything, including water, that can accept a proton, or that can donate a proton to a base, can be considered to be an acid. So you have to label acids and bases. And then the other thing we did was conjugate acid-base pairs. So once the hard part really is deciding what's the acid and what's the base. Once you do that, then try not to overthink this, okay? So conjugate acid-base pairs, they are related by proton transfer. So you're not pairing up the acids and pairing up the bases. What you're saying is, the way we wrote this NH3 base accepted a proton to become this acid. So these are a pair, a base and an acid together, related by proton transfer. So here, this is the same example. So if you just want to quickly go in, base, acid, acid, base. If it bothers you, it's not double, make it double. The arrow. And now you have two choices, okay? So you can write it out. So NH3 accepted a proton to become NH4 plus. So those two substances are related by proton transfer. Yes, you can write it out what we did last year. You can also do this. So that is more than enough to say that they're a conjugate pair. Okay, but I'll do the same thing. So then HCl donated a proton . So a conjugate acid-base pair has one acid and one base. Don't pair up the acids and pair up the bases. And try not to overthink it either. The NH3 and NH4, they're not exactly the same, but they look pretty similar to each other, right? They are related by proton transfer. HCl, Cl minus. Okay, so you're looking for the substances that are related to each other. Okay, so that's really what you would have, that's something that we would have done in grade 11, okay? So now what we're going to do is sort of switch a little bit and do more what's expected in grade 12. So the next example is to write, we're going to write the dissociation equations for phosphoric acid. So now you are going to make your own. Okay? We're going to do phosphoric acid. So it does tell you that it's an acid. So that's a clue. Okay, it literally says acid. That means proton donor. And when you write dissociation equations, now chemists are lazy. So eventually, you're going to see why when we do ice tables, maybe you want to leave the water out. But technically, when you dissociate something, what are you dissociating it in? Water. So when you write dissociation equations for acids and bases, water is always going to be the other reactant. These things would all be aqueous eventually, but I'm just going to leave that out because I don't want to clutter this slide, okay? It doesn't really matter when you do this, whether you use a double arrow or not. When we figure out the acids and bases, maybe it makes more sense to you to use a double arrow. It's up to you. So it says write the complete series of dissociation equations for phosphoric acid because phosphoric acid is special. How many hydrogens does phosphoric acid have? 3. So what that means is we are going to have to do 3 dissociation equations. Do one at a time, okay? So this is called a polyprotic acid, polyproton, more than one. So when this is fine, you can handle this, but when we go to do the math, having a polyprotic acid makes things much more difficult. So that's what you would do next year, okay? When we do the math, we're only going to, like the ice tables and the equilibrium math, we're only going to deal with monoprotic acids and bases that have only one one proton gained. Okay, so now we are going to dissociate. So each time, if you have an acid is going to donate. Now, if you don't like the word donate, then write giveaway. Okay, so we're going to give away an H to make it H2. But if you give away a positive, then you become negative. So every time you give away a positive charge, you're going to become more negative. Every time you gain a positive charge, you become more positive. And now what happens to the water? So there was this special ion, and once they could discover that this ion was formed in water, then again they had to expand their definition to proton transfer, okay? So the other substance sorry, it's supposed to be like this should go in there. I didn't leave enough room. The other product is H3O plus. And this is a special ion from grade 11. Ooh. which is called the hydronium ion. It will always be H3O plus. So water can accept a proton, so it acts like a base to become H3O plus. So if you want, even number them. This is equation 1. Now we're going to get rid of the second proton. So we're going to start with this. Always water. Water is going to accept. And then we're going to get rid of an H. So what do we have now? HPO4 and 2 negative, because it's given away 2 positives. And we still have an H. We can do it one more time. Now we're at PO4. 3 negative. And H3O plus. I'm going to refrain from labeling acids and bases. We're going to talk about some of these items when we get to the word amphoteric. So for now, depending on what the question says, it says to just write the complete series. So really that's what we've done. We've gotten rid of all of the H's. So then if you were asked to write an overall equation, it's really going to be one line. You can just kind of sneak it in the bottom. Are there substances we can cross out? Reactant, product, reactant, product, reactant. Those things will be canceled out like we did before. And the overall equation actually makes a lot of sense. If you have phosphoric acid, which has 3 hydrogens, how many waters do you need? 3? 1, 2, 3? So it's going to donate 3 of its protons to make phosphate. So this is the phosphate ion, right? Which would be on the back of your periodic table. So you could even check it that way too to see what you should end up with. And then how many hydroniums do you make? 1, 2, 3. So if this was HCl, we would only do it once. Say H2SO4, sulfuric acid, you would only do it twice. And you're limited by the charge, right? So the highest charge is usually -3, so then you can't go beyond that. You would only do 3 of these maximum. Okay. So when you write equations, what you'll find is there are some substances that can actually be both. So the word or the prefix amph, like an amphibian, right? So amphibians can live on water and land. It implies duality. So amphoteric means that something can be acidic or basic. And the most common example is water. So let's do, this is hydrochloric acid, so I picked it on purpose. Hopefully you recognize that. So then logically, if hydrochloric acid is reacting with water, then the acid has to be the acid. It's going to be the proton donor. And water can be a proton acceptor. You just saw that. It can make what we call the hydronium ion. So HCl donates, and then water accepts. But water can also donate protons to bases. So ammonia is a base. If water donates, actually I'm doing it right. If water donates a proton, what would be left if you subtracted a proton from this? Pardon? Okay, so one of the things, again, depending on your grade 11 experience, it's really important to kind of think of water as HOH, okay? If it donates a proton, then we write what's left as OH. Maybe we talked about this with displacement, that's how you figure out like that the hydrogen can switch with the metal and stuff like that. Okay, so here, water reacting with an acid, it behaves like a base. It's going to be a proton acceptor. Water can also react with a base to be a proton donor. Doesn't have to be water. Okay, so the next box or slide or whatever says, let's go back to the phosphoric acid example. Are there substances that are amphoteric? Okay. So if you have a different color, let's just quickly go in and label what's an acid and what's a base. So, again, the word acid is literally in the question. So this is definitely an acid. And we're trying to show that that we are giving away a proton each time. So all of these are acids. But in order to show both, then it needs to appear twice. So we're looking at the substances really that appear twice, okay? Technically, in this case, water is not amphoteric. It's a base every time. However, if you think of reversibility, if we go this way, what is this substance doing? H2PO4 negative. It's becoming H3PO4. Did it gain a proton? Yes, it did. So this is a base. Here it's a base, but down here it dissociated and donated. It's an acid. So let's take a look at this one. This is an acid. It has 2 hydrogens. It donated. Now it only has 1. But when you go backwards, now it's got 1 and it accepted 1 to now have 2. So this is a base. But then we said, wait, well, it can still donate an acid. or donate a proton, so it's an acid. So what I'm going to do, it doesn't really matter. Both of them are very similar. I'm going to go to that other slide where there's the blank spot. These two substances are really similar, okay? So the reason that they are amphoteric, in order to be an acid, you have to have a proton to donate. Do these have a proton to donate? Yes. And opposites attract in chemistry. It's got a negative charge, which means positives it loves positives, so it can also be an acceptor. So anything that's got both H and at least one H and a negative charge can be amphoteric, also water. But there is, you might have actually already discussed or thought about this depending on what you're into. Let's say you're into health and how your body works. We have what's called a bicarbonate buffer in our blood. So it goes between, this is bicarbonate. So you put baking soda with vinegar and it makes an acid-base reaction, right? So this can accept a proton to become carbonic acid. Okay, so let's say you eat something acidic, super acidic, or something happens in your body that's super acidic, that releases too many protons. This molecule in your blood can accept those protons, and then it can also donate to become the carbonate ion. This carbonate with acid is bad for the ocean. This is what's, if you've ever heard the term ocean acidification, this is basically what's occurring, that carbonate molecules in the ocean, like in coral, in the shells of molecules that, or not molecules, organisms that have exoskeletons, they are being bombarded by, due to the carbon dioxide dissolving in the water, they're being bombarded by protons, which is affecting the carbonate in their shells and making them less hard. It's killing the coral. It's affecting the carbonate levels in the coral. So this is another example as well. This does not apply to the phosphoric but acid example, but maybe you've heard of this. And you'll talk about, again, the blood buffer and homeostasis if you take grade 12 bio. Okay? So I almost actually took this off, but um, it really sort of emphasizes the idea that when you have substances reacting together, there is a great potential for proton transfer. It doesn't have to be what you would normally think of as a neutralization reaction. And it's unfortunate because one of the first things you probably did as a kid was put baking soda and vinegar together in your classroom and make the bubbles, right? The volcano or whatever. It's so easy to do. And that's a traditional acid-base reaction. You're neutralizing the acid. But really, when you have something that can accept or donate a proton, technically, that's really what an acid-base reaction is. So water can auto-ionize itself. And the reason this matters is because when you measure the pH of a solution, most people would think, oh, I'm going to measure H or OH only. And again, what they found was you can actually find concentrations of both. And sometimes it's a teeny, teeny, weeny, tiny amount. However, it's still in there. And it comes from this reaction. So it doesn't really matter which one you think of. There's two waters here. It's not like the waters in the flask are like, okay, I'm going to be the acid. I'm going to donate my proton. You be the base and accept it, okay? They obviously don't talk to each other, yes? So pick whatever one you want. If you want these two to go together, that's fine. So now let's say this water became H3O plus, so it accepted. So this is the base. Then it would have taken the proton from this water, which became OH. So we'll call this the acid. But again, it really doesn't matter. I just went in order, okay? So then this one goes with this one. So now this is the donor. And then this one goes with this one. And OH, traditionally, you would think of that as basic. So when you do questions with concentration, then if it's a perfectly neutral solution, these two ion concentrations are equal. But if something is acidic, what they found was, yes, there is a greater concentration of hydrogen ions, but there's also a tiny bit of hydroxide. And where does that hydroxide come from? The auto-ionization of water. So if this is, say, 0.01, this would be like 2 times 10 to the power of negative 9, like a tiny number, but it's not 0. It's still there. And then if it's a basic solution, then the hydroxide ion concentration is greater. So when you do the questions in the homework, one of the things you can use is the water ionization constant because, again, it's just products over reactants. Do we include liquids in the equilibrium law? No. So one more thing. Again, lazy chemists. So hydronium and hydrogen ion, the proton formula, are used interchangeably, okay? So that's why here it's just written as H+. Even in a normal, non-coronavirus time, you would be given this value, 1 times 10 to the negative 14. It comes from that a neutral solution has a pH of 7. So then these two are equal, so they're 1 times 10 to the negative 7. And I'll show you how to convert pH into concentration. So if you have an acid, you can use this number and whatever the hydrogen ion concentration is to find the OH. Like just simply rearrange it, divide, and vice versa. If you have a base, you can use the OH concentration to find the concentration of H+. The next few slides really just have formulas. So if you wrote down that exam information we wrote down before lunch, the pH formulas, those were all listed there. Again, even if it was a normal semester, I would give you those, okay? So these two things here, Now, it's unfortunate that not very many of you have gotten to the end of functions yet. So one of the topics you're gonna do in functions is log, okay? So this calculation itself is actually super easy. However, you have to know how to use your calculator, okay? So it's not negative log times the H plus concentration. It's negative log, and then you just put in the hydrogen ion concentration. If you don't, your calculator will give you an error. Logs, the natural log it's called, has a base of 10. So to do the inverse operation, it's actually 10 to the power of negative pH. If you look at your calculator, it says log, and then above it says 10 to the x, because that's the inverse of log. So you can use that button to help you. So the calculations themselves are not that difficult. It's really more that you know how to use your calculator, okay? So when you do these questions, if you need me to show you, I most certainly can. Okay, and then we can also do something called POH. So there is more than one way to convert between values, and because there is a considerable, proton transfer, the basic side and the acidic side go hand in hand, then often the questions will be like, here's a concentration. Find pH, find POH, find H+, find OH, and you can do all of those things with very little information, okay? So again, negative log, and then whatever the base concentration is, and then the inverse of log is 10 to the power of negative POH. Whenever we don't deal with a POH scale, right? That's not a thing. So whenever you have a base question, there's always going to be one more step. You can change POH into pH. So pH plus pH plus POH is 14, because we don't have a POH scale. So you always want to change it. So maybe highlight these ones. So these were the equations that were given in that exam info we wrote about before lunch. Okay, so when you have a strong substance, then determining the pH is really, really easy, because a strong acid dissociates 100%. Thank you. And I got your email. Thank you. Bye. So when you do these equations, yes, you can include water, and then you get H3O+, But like I said, chemists are lazy. Okay, so we are going to use H plus and H3O plus interchangeably. And we're also going to streamline stoichiometry. Okay, so it says that the concentration of this is 2.5. If this is 1, a coefficient of 1, and the hydrogen is a coefficient of 1, then it's the same. Similar to, actually, I wrote this on the board yesterday, right? Where I cheated. So what's the concentration of hydrogen? Its coefficient is 1. The concentration of HNO3, its coefficient is 1. And what would you get? 2.5, okay? Do we care about the nitrate? No, it is a spectator ion. It is not about the proton transfer, it's about the hydrogen. It is not about transferring nitrates, okay? So this is a spectator. Yes, it would be the same, but we don't care because we're just finding pH. So if you have never used the log button on your calculator, give it a try so that you can get used to it. So if you don't get that, let me know. Now, students will also say, Ms. Todd, isn't the pH scale from 0 to 14? Maybe your teacher even said 1 to 14. So the pH scale is for things like, what's the pH of my shampoo? What's the pH of the milk I'm drinking? What's the pH of coffee? What should the pH of my blood be? What's the pH in my hot tub or my pool? If you at your house had a 2.5 molar solution of nitric acid, we would have some questions for you, okay? This is not a we don't even have nitric acid at school. It has to be stored separately. This is a very strong acid. So this is a very strong concentrated solution, which is not a practical thing, okay? So just plug it in and you'll get your answer. If it helps you, then you can add into here. So nitric acid, again, can be used to, as the nitrate part of it can be used to make explosives. So if you had 2.5 molar nitric acid, somebody would have some questions for you. So it's very strong. Okay, so we're going to determine the pOH of a 0.35 molar solution of barium hydroxide. So again, it doesn't say strong base here, but strong bases have hydroxide in their formula. So how many hydroxide ions are there? What should I put out front here? 2, okay? So now this time, this is 0.35 molar, so you have to multiply by 2. Picture mask. So again, in this case, most people will be like, Ms. Todd, this is a base. Bases should have a high pH. pOH and pH are not the same thing. So you could go this question says to stop at pOH, but if this was a legitimate situation and you wanted to know how it was on the scale, then you would use this one, which you're given, okay? It was one of the ones you highlighted as well. So pH would be 14 minus pOH. Which makes a lot more sense. 13.85. Okay, that's a high pH. That makes sense. Shh. Picture mask. So like I said, you can do lots of weird calculations with very little information. So now we're going to find the H+. So there are 2 ways you can do this. Now that we have pH, you can do (10 to the negative pH), or you can do this one. You'll get the same answer. Okay, so you pick what you like. If it's a base, it should be a tiny number, right? We don't want a lot of hydrogen ions. People generally usually choose to do it this way because this way you have to use scientific notation. Most students don't like that, but you get the same answer. It doesn't matter. You would be given this equation, given the Kw constant, you'd be given that H+ concentration equation, you'd be given this equation. So you just have to know how to plug it in. And again, you have to kind of know how to use log on your calculator, okay?